Hello and welcome to Cannon County High School Algebra 2. It is Friday, and so we're going to end the week with a nice easy lesson today. We are going to begin our discussion on probability distributions. And so we're actually going to do two different IXLs today, but neither one is all that challenging. It's kind of an introduction to probability distributions. And to start out, we need to know a little bit of vocabulary. And so we're going to start out talking about the difference between discrete and continuous. So, Mr. Lyon, it won't be long at all. I hear the governor is giving a speech soon, so we'll see what happens. You sit over there for a little bit. And first, let's define the difference between discrete variables and continuous. Discrete means finite, or it can be counted. Continuous means infinite, and it cannot be counted. So what does that mean? Well, here's an example of a discrete variable. Let's say X is the number of people at a Titans game. Could you actually count up the number of people at a Titans game? You could. It would take a long time, but you could actually count exactly how many people are at a Titans game. It might be 74,127, but you could actually count them. So that would be an example of a discrete variable. A continuous variable is something like, what's the amount of time that you spend on average playing video games? Now, you might say, well, that sounds like I could actually count that up, but it depends on what you're using to count it with. Because if you say, well, I normally spend an hour and a half playing video games every day. Well, is it an hour and a half, or was it 1.499 hours? Or was it 1.499173 hours? So you can get even more and more precise. There is an infinite number of times that you could write down for how long you're playing video games each day. But there's not an infinite number of numbers that you can write down for how many people went to a Titans game. There is an actual number that you could count. If it's continuous, that means you can't really count it. Time is something that's very difficult to count. We can chop time up into small units, but if you say, I'm going to write a sample space of all the times that something can happen, well, time is a continuous thing. It moves and it flows. It doesn't have concrete building blocks. So that's kind of the difference. And what I'd like to do is just start out looking at a couple of these. This is from DD.1. And let's just try a couple. After you do a couple, I think, like I said, this is going to be pretty easy. You're gonna see how this works. A probability teacher is rolling a die. Z is the distance it lands from the teacher. Discrete or continuous? Is distance discrete or continuous? Well, distance is kind of like time. It all depends on how precise you want to measure. Are you rounding to the nearest foot? Are you rounding to the nearest 1/1,000,000th of an inch? It's continuous. You can't really count up. You could say, well, I'm going to count to the millionths of an inch. Well, then the next person could say, I could count to the 100 millionths of an inch, and so on. There's an infinite number of distances that the die could land from the teacher, so that's continuous. Get the idea? Why is the number of keys on a randomly chosen keyboard? Okay, no matter what the keyboard, could you actually count how many keys are on the keyboard? Yes, you could. Therefore, that's discrete. The number of keys on a keyboard is discrete because we could actually count them. So really, that's what you're asking yourself. I'm going to jump up a few levels here, and I don't think it can really. It says this skill only has one level. Okay, well, there you go. See, like I said, it's not going to. Let's do one more. X is the number of classes a randomly chosen student is taking. What do you think? Discrete or continuous? Could we actually count how many classes you're taking? Or is it a continuous, infinite number of classes that you're taking? No, it's discrete. You could actually say, well, I'm taking 6 classes, and that's discrete. So you get the idea. Now, I'm going to go back, and we're going to go to DD.2, because this is the one where we're actually going to start building sample spaces. So this one is called write a discrete probability distribution. So you're used to frequency tables, and that's really what this is, but we're going to use frequency tables to construct a probability distribution. It's not difficult, it's just a way of organizing, and again, this is discrete, so we should be able to actually add these up. So that's what we're going to do. An employee at a craft store counted the number of red buttons in each bag of mixed buttons. And so here we go. The number of red buttons, number of bags. X is the number of red buttons that a randomly chosen bag had. Write the probability distribution of X in the table below. So they're saying this bag had 32 buttons. This bag had 171, and so on and so on. But they have calculated the probability then of each one of these. How did they do that? Well, they added up what all of these add up to. What do all those add up to? Well, I could use my calculator to do this, but there's actually an easier way, because what do the probabilities of each one of these discrete variables, what do they have to add up to? They have to add up to 1, right? So if they give me 3 of the 4, could I figure out the fourth one just by subtracting from 1? Yes, I could. So what do the other probabilities add up to? 0.4, 0.3, and 0.2. Those add up to 0.9. Therefore, the only missing probability here, this one, has to be 0.1. Now, I know that's the right answer because I know that these have to add up to 1. But could I have done it the hard way and actually added all these up and divide 32 by the number of that these all add up to? I think I could. So let's go on to the next one. Actually, let's jump up a level because this problem looks almost identical to the one we just did. All right, this one's a little bit different. After trying out a new fertilizer, a farmer counted the number of blueberries on each of his bushes. Okay, so again, they've given us a frequency table, and we want to write a probability distribution. All right, so let's see. X is the number of blueberries that a randomly chosen bush has. Write the probability distribution of X in the table below. Well, this one, there's 2 of them, so I can't just subtract from 1, so that's not going to work this time. But how many bushes are there? 6, 3, 3, 4, and 4. Well, 6 and 3 is 9, 12, 16, 20. There's 20 total, right? So we want to figure out, for 785, what's 3 out of the 20? Well, what is 3 divided by 20? Well, if you want to bust out the calculator, now would be a good time. 3 divided by 20 is 0.15. So that means that this one has a probability of 0.15. And for 860, this one right here, that's 4 out of 20. Well, you could do that on your calculator, but if this one's 4 out of 20, then that one's 4 out of 20, then if that one's 0.2, then that one also has to be 0.2. And what do all these probabilities have to add up to? That's right, they've got to add up to 1. Okay, so that one looks the same. Let's jump up another level and see what happens here. All right, this one, they want us to find all of them. Okay, Neil counted the number of desks in each classroom at his school. X is the number of desks that a randomly chosen classroom has. Write the probability distribution of X in the table below. Well, we have to just actually figure out the probability of everything in the sample space. So this shouldn't take us too long because these numbers don't look too bad. For 18, the number of desks was 18. That's 3 out of how many? Well, 3 and 4 is 7. 7 plus 4 is 11. 11 plus 5 is 16. 16 plus 4 is 20. So we have 20 again. Well, that means this one is 3 out of 20. Well, we just did that on the previous problem. 3 out of 20 is 0.15. All right, the next one, 4 out of 20. Well, again, from the previous problem, we know that 4 out of 20 is 0.2, 20%. 4 out of 20 again. So you see what we're doing here. We're just kind of constructing our discrete probability distribution. Let's see, 5 out of 20. 5 out of 20 sounds like a quarter, so that's 0.25. And then we have a 4 out of 20 again. So that's 0.2. And again, you could check your answer and just make sure that all of these probabilities add up to 1, and they do. Okay? So click submit, which I thought I did already, but sometimes this computer goes slowly. There we go. Let's see if that's any different. Let me get to a different type of problem. Nope, that's the same type of problem. Let's go to one that's a little bit tougher. Let's see, that is the same type of problem again, so I'm not gonna bore you by doing the same problem over and over again. Let's see if they've got a different one here. There we go, there's a different one. This will be our last one. We're up to 85. Let's see, the employees at Danny's Construction monitored the number of cracked window panes in each shipment that they received. Okay, cracked panes per shipment. X is the number of cracked panes that a randomly chosen shipment had. Write the probability distribution of X in the table below. Write each probability as a decimal. Okay, well, there's two ways we can do that. First of all, they didn't give us a frequency table this time. This time they actually just gave us the raw data. But we could figure it out. I mean, this means that for 575, there's 1, 2, 3, 4, 5, 6, 7, 8. There's 8 of those. 8 out of how many? Well, let's see, 9, 10, 11, 12, 13, 14, 15, 16, 17. Out of 25. So that means there's 8 out of 25. So 8 out of 25, that's the 0.32, right? Let's try that and make sure. What is 8 out of 25? 8 out of 25. There it is, it's 0.32. So that is how they figured out that this is 0.32. So we could do this with each one of them. They want us to figure out 951, so that would be 1, 2, 3, 4, 5. Okay? Or you could do what? Exactly. You could either take 5 out of, what did we say this was? Yeah, we could do that, or we could just subtract these from 1. Whichever way you want to do it, it doesn't really matter. Let's do it the other way just for fun. Let's take 1 minus 0.32 minus 0.2 minus 0.28. And that gives us 0.2. Which is the same thing we would have gotten if we would have taken 1, 2, 3, 4, 5. 5 divided by 25 is 0.2. Okay? So like I said, it's Friday. We're doing an easy lesson. Try DD2 and DD1. DD1 is just having you distinguish between discrete and continuous, and DD2 is just having you fill in a probability distribution. This is all kind of laying the groundwork for more complicated distributions that we'll work on next week. But we're taking it easy because it's Friday, so that's all right. If you have any questions or comments, just put them down in the comments below, and thanks for watching. Have a great weekend. Bye.